Hi everyone! So with this video we are ready to explore yet another application of non-zero temperature QCD on the lattice. Specifically, I want to argue with this set of slides and video that one can go beyond mapping out phase diagrams and look into the thermodynamics of QCD at non-zero temperature. So we are at this stage exploring the equation of state. We will continue in the next days with other application, but let's focus on equation of state first. So first thing I need to tell you is what is the equation of state. The equation of state is the functional relationship among thermodynamic parameters of QCD at equilibrium. In particular, the relevant parameters are the temperature, the volume, and the chemical potentials, and what goes under the name of equation of state in a broader sense are measurements of the pressure, the trace anomaly, the energy or entropy density at equilibrium. What we want to know is basically the dependence of these quantities on the thermodynamic variables, because we need that for a faithful description of, for example, the expansion of the plasma in heavy ion collision experiments or in cosmology about the evolution of the early universe. As usual, we want to think about the limiting behaviors first, where we can learn something from, for example, perturbation theory or effective low energy models. In particular, in the limit in which the temperature is sent to infinity, low orders of perturbation theory may give a reasonable answer, but there, of course, we have no experiments that can possibly reach such high temperatures in order to confirm the guess made on the basis of perturbation theory. At the order of 10 times the deconfinement temperature, we can also do something with analytic or perturbation theory based technique. However, we need very high order diagrams that can be computed in a framework that takes into account dimensional reduction or efficient resummation schemes like the hard thermal loops, and only in that case there is some predicting power. At the other edge, we can send the temperature to 0, and in that case we have some models that work pretty well in describing the behavior, the thermodynamic behavior of our QCD system, and these are glue ball in pure Young-Mills or hadron in full QCD resonance gas models. Okay, and what do we learn from these limiting behaviors in full QCD? Well, for the limiting behaviors where T goes to infinity, we basically have a free gas of quarks and gluons, and we can consider these as an expression for the pressure in that case, while as T goes to 0, we basically have a gas of free pions, for which the expression of the pressure is also reported on the slide. Then, naively and without imagining more complicated scenarios, what one would expect is that the pressure grows across the transition temperature, and this makes sense because it would reflect the fact that a larger number of degrees of freedom are actually liberated at Tc as soon as we cross the phase boundary. Now, of course, we are interested in the answer to the full interacting case, and if the goal is then obtaining the free energy density from the full QCD partition function, we want to obtain that from Monte Carlo simulations and from lattice QCD. However, there is an obstacle, and it is that in Monte Carlo simulations, all expectation values, as we wrote down many times so far, were all normalized to Z, which means that Z is not something that we can directly access or compute. And then we have to think about alternatives. In particular, one can measure the expectation value of some observable and use that in order to access the partition function indirectly. How would one do that? A method could consist, for example, in calculating the derivatives of the partition function with respect to some parameters, as in the derivative and integral methods that we will discuss in a moment in two different approaches, which are called fixed n-tau or fixed scale approach, or obtaining thermodynamic potentials from momentum distributions, which is another method that I will not cover in these slides, through which you can get to the equation of state. Remarks. As I said, there are two possibilities to tackle this issue with the integral method, for example, and the point is that we want to extract thermodynamics with good resolutions in temperature over wide temperature ranges. And we know how the temperature is controlled by the lattice spacing and by the temporal extent of our lattice. Then, if we imagine to tune the temperature by the coupling beta, we know that this is going to ensure us a better resolution, but it leads, for reasons that we will discuss in a moment, to different cutoff errors for different temperatures, because then coarse lattices would be considered in the low temperature region. The other possibility is to tune the temperature by n-tau, and there we have a loss in resolution because this only allows for discrete temperature steps. So unless we are able to simulate on very fine lattices, then we don't get reasonable temperature steps for the desired resolution. Anyway, let's go through the methods. And the first one I mentioned was the derivative method. Which is the most direct way to extract thermodynamics from simulations, and it was proposed and used long ago. So basically, with that method, we can get to results for the energy density as well as to results for the pressure and all other thermodynamic observables that I mentioned in the beginning. However, there is a caveat to employing this derivative method. And the caveat stands in the fact that we know the relation between T and n-tau and the lattice spacing. And for decently large values of n-tau, if we want to still limit the costs in our simulation, the only way is to resort to anisotropic lattice spacings. So you are familiar with the concept of lattice spacing as the minimal distance in our lattice that separates two contiguous sites. And what you can do is you can set different lattice spacings for the spatial and temporal directions respectively. And if you pick a finer lattice spacing in temporal direction, then by changing n-tau and going to large n-tau, you don't increase the simulation costs so much in order to fulfill the chain of inequalities that I told you is very important in running finite temperature simulations, where you know that n sigma, the spatial extent, must be much larger than n-tau. Okay, and then with this definition for the energy density and pressure density in mind, what we have to do is we obtain the lattice versions of the density and pressure just by using their definition and the partition function as we know it in our specific case for QCD. This formula that I have on the slide are the lattice version of the energy density and pressure, where also the anisotropicity coefficient Xi appears, which is the ratio of the two lattice spacings. When you work on the derivatives explicitly, you realize that you need the beta functions of the gauge couplings and of Xi, as well as for the running of the quark masses if quarks are included. And this is the second caveat of this method, because then beta functions must be determined and you can do something perturbatively, but if you want to be accurate, then you need to resort to lattice techniques also for that purpose, and the calculation is becoming very soon very complicated. And if I had to mention a third caveat still about this method, it would be that it is things are becoming more complicated because of the fact that you have more free parameters that you have to tune in your simulations to, for example, stay on some line of constant physics and make sure that while you take the continuum limit, you are always computing the energy density and the pressure on that line of constant physics, such that the renormalized masses of bound states and particles are kept constant. Therefore, since there are so many caveats, it will not come as a surprise that the most used method is actually not this one, but rather the integral method. In the integral method, what you do is you take derivatives of f with respect to some parameters, and these are serving as observable, and then you integrate them back again in order to obtain the free energy or the free energy density, which I'm indicating by a small f. So it basically works as in this equation that I have on the slide, where the x in the integrand on the right-hand side is basically the temperature that then gets integrated from T0 to T, and you obtain the T dependence. This can be done in a fixed NT approach, so in an approach in which the temperature is tuned by changing beta. In that case, it is convenient to take derivatives with respect to bare lattice parameters, and the bare lattice parameters in a full QCD simulations are the coupling beta and the masses of the fermions included in our simulations. So you can see the same expression as above, but this time instead of having T and T0, we have the pair of beta and bare quark masses, and the same pair at a reference value. Another comment I want to make on this expression for the free energy density, or some difference of free energy density, is that also some subtraction is included in both cases in order to achieve, to ensure renormalization of the free energy and of the pressure such that they are zero at zero temperature. Okay, and then you want, next thing you want to do is you want to perform the integration. And for the integration, you want to stay on a line of constant physics, which is basically the function beta as a function of mf that ensures you that the renormalized quark masses are constant throughout your investigation. And then at that point, you are done. After you have done this type of integration, you obtain on the left-hand side basically the difference between the renormalized free energy density at two different values of the temperature, because that's the only thing that changes in the two cases for beta mf as opposed to beta 0 mf 0. So you have an integration constant on the left-hand side. And this is something that you normally can fix by, for example, matching your results at low temperatures with some hadron or gluon resonance model that you know works well in that limit. Okay, still sounds a little bit complicated, doesn't it? However, one can figure that exactly this type of derivatives are appearing in the expression for one quantity, which is called the trace anomaly, or equivalently the interaction measure. This quantity can be expressed exactly in terms of the same derivative that appear before integration in this integral that you want to measure. Let us remind ourselves what is the trace anomaly. In a relativistic system, the energy momentum tensor for a liquid or gas has this expression that I'm reporting on the slide, where u mu is the forward velocity of a volume element in the rest frame of the medium. In this context, the trace anomaly is just the trace of this tensor, and one can work out expressions for the trace anomaly, where you can see that it is basically a temperature dependence of the pressure over T to the power of 4, and one can even work it out explicitly and see that it is some specific combination between the energy density and the pressure density. Okay, so what do you do? After you have converted t derivatives into a derivatives, and if you know the beta functions and line of constant physics, you can compute the interaction measure directly. As you can see, we have the same exact derivatives as we had in the expression for the free energy density that is our final goal. And on top of that, we need to take these derivatives, d beta over dA or dmf over dA. So we need to know, again, the beta functions and the line of constant physics. But if that's the case, then the most direct way to proceed is to calculate the interaction measure. And this leaves you with something which very closely resembles the integrand in your formula for the free energy density. So what is left afterwards is you need to interpolate this interaction measure or trace anomaly, after which you can numerically integrate and obtain the pressure out of it. So far we have seen how the interaction measure integral method works in a fixed n-tau approach. But as I mentioned from the beginning, there is an alternative, and this is called the fixed scale approach that has also been used in the literature. This approach consists in keeping the coupling and therefore also the lattice spacing constant while varying the temporal lattice extent in order to tune the temperature through that. We already discussed that this leads to discrete temperature steps and that interesting resolutions in temperature then demand increasingly fine lattices. The other consequence of this change of approach is that then one wants to take temperature instead of beta as an integration variable. And this is done while holding beta fixed. That is to say that basically we are integrating over n-tau. And at that point, this requires an interpolation to real n-tau because n-tau is the temporal extent in the time direction. So it is a discrete and integer variable, and we need an interpolation to real n-tau. Other than that, the computation goes like we said a moment ago, that you first directly measure the interaction measure, and then you integrate it out in order to get the pressure according to known thermodynamic relations. At this point, you have two alternatives. So what should you use, fixed n-tau or fixed scale? In order to make a decision, let's go through the advantages and disadvantages of both methods. So the fixed n-tau, which is what we discussed before, has the advantage of ensuring a higher resolution in temperature, but it then requires renormalizations for every value of the coupling. That is, per every value of beta, we also have to run a zero temperature simulation, which requires a very large extent of the lattice in the temporal direction in order to know what to subtract in our integrands in order to achieve renormalization. The other disadvantage is that you have a different lattice spacing and therefore different cutoff effects when you simulate at different temperatures, and particularly you would be trying or attempting continuum extrapolations starting from different values and having particularly coarser lattices when it comes to small temperatures. So all in, you would have a quality of your continuum extrapolation which would be temperature dependent. Let's move to the fixed scale and see what are the advantages and disadvantages of this alternative approach. It has large discretization effects as soon as the temperature is above the inverse lattice spacing, which means that the thermal fluctuations are basically on the scale of the cutoff. However, it has the advantage that if you do not tune beta at all, then you need no tuning to keep the temperature fixed on the same line of constant physics, and also one t equals 0 simulation on a very large nt would be enough in order to be able to renormalize all observables. So in the end of the day, one should rather say that the two approaches are complementary and both of them are used. We have argued that This works better at large temperature, or rather it works worse at small temperatures, but this also has some complications at large temperatures. So fixed scale is better at low T, fixed and tau is better at large T. By using both, we get complementary information, and we can also cross-check in the overlapping applicability regime the two different methods. Okay, and I would like to wrap up this video by showing you some results for the calculation of the equation of state, starting from pure gauge theory, so SU3 Young-Mills. And here I am citing a result dating back to 2012, where the pressure was computed after the continuum limit was taken for an aspect ratio of 8, starting from this set of raw data that have been plotted in a log-log scale, and where the interaction measure was rescaled by T over Tc squared in order to make more evident what are the deviations from the perturbative HR thermal loop at next to leading order, or OG to the 5 behavior from the perturbative regime. So basically we see that for T greater or equal to 10 times the deconfinement region, we finally access the regime where we can fit the G to the power of 6 coefficient of the perturbative expansion. And this is what was done once the pressure was computed in this paper. And also a parametrization was obtained across the gluon plasma phase. Another important remark is that even at the largest explored temperature, the pressure is still 10% below the ideal gas limit, and this tells us that the approach to the ideal gas limit is rather slow. I also have on my final slide for this video for you some results that have been obtained for the equation of state in full QCD. So you see on the left with some fermion discretization, which is East fermion in 2+1 at the physical mass, the results for the pressure density, energy density, and entropy density. You again see that the hadron resonance gas works rather well till Tc. On the right, you have results that have been obtained with an alternative staggered fermion discretization, and in a setup with changing the number of active flavors. Again, HRG works well at small temperatures, and changing the flavor content changes the height of the set when it comes to measuring, as in this plot, the trace anomaly. And with that, I would like to conclude about the equation of state. You will get a chance to work a little bit on the different approaches to obtain the equation of state with specific reference to this paper and data taken from this paper. In the case of pure Young-Mills, where you don't have many complications that come from going to the case of full QCD. And I hope you have fun with that assignment.